Laser scanning imaging has been widely applied to many different applications. So for example, that could be used in medical or clinical diagnosis and also the basic biological science research or material science research. And also that could be used for machine vision in the manufacturing industry. So current gold standards of laser scanning technology is primarily based on mechanical scanning mirrors to steer the laser beam directions. However, the scanning speed are primarily limited by the mechanical inertia, and that could only reach up to the speed of around tens or 100,000 line scans per second. So now we have a technology called phase that could overcome the limitations of the current technologies, and that could provide at least 100 times faster in the scan speed. And when it's applied to the laser scanning imaging applications, we can also preserve the very high image resolution at such a high speed.
At the heart of this new technique is the infinity mirror, a pair of parallel mirrors, but one mirror is tilted with a tiny angle of 0.01 degree. This mirror pair transforms an ultra-short laser pulse into many smaller pulses, bouncing between the mirrors and return backward. This is similar to our daily experience with a mirror pair, between which we observe multiple virtual images of ourselves. Likewise, the device generates virtual pulsed sources as they are launched from different positions at different times. These pulses are then projected onto a specimen, behaving as a scanning optical beam for laser scanning imaging. It can be used for imaging and analyzing single biological cells flowing in a microfluidic channel at high throughput, especially useful for detecting rare cancer cells. The optical pulses effectively perform line scanning imaging as the cell flows in the microfluidic channel. At a scanning rate of 80 million line scans per second, it does allow high throughput imaging of cells.
So being 100 times faster in imaging speed than the state-of-the-art technology and without losing the image information content, our technology could be combined with the microfluidic technologies and become an effective and efficient tool to analyze individual cells such as cancer cells in a great detail within a very large populations of cells. It could open new potentials where the high-speed and high-throughput biological microscopy are needed, but were once impossible. For example, they could be used in imaging flow cytometry for the cancer screening. You can also use the technology for the whole slide imaging for the routine histopathology. You can also use it for the large-scale microalgae screening for the harmful algal bloom, which is popularly known as red tide in the marine biological research. And the technology could also be used to monitor the high-speed cellular dynamics, such as the neuronal firing events that could be used to study the complex brain functions and diseases.